Hi everyone, it's Mr. Kwan here. Today we're going to continue talking about regression. Now, in a previous video I talked about how to do regression in Microsoft Excel, and the sample data that we used was around COVID-19, and we actually took real data from the World Health Organization off their website and did some regression there. So if you haven't already seen that video, pop over and watch that video and then come back and watch this one. So as we stated before, regression is a way we can calculate between all points provided on a scatter plot the best average. And the mathematical process to find the best fit functions for the given data points is quite tedious and also outside the scope of this class. The good news is that many calculators and Desmos will do the regression calculations for us, and it's important to just try to recognize when we look at our scattergram or scatter plot what the general shape of our data points are. So this is a list of steps on how to do your regression in your calculator. Please do note that it needs to be a Texas Instrument calculator. If you have a different type of graphing calculator, you're either going to have to use Microsoft Excel or Desmos, or research on your own how to utilize your specific brand of graphing calculator to do regression on it. So I'm going to let you skim over this. I'm going to kind of quickly pass over it. It's here for you to refer back to so that you can follow through these steps. Let's go ahead and move on straight to our first example. It says the table below shows the US plastic bottle water sales in billions since 1996. And the first question asks, what type of function will model this data the best? And I think what will help us do that is if we create a scatter plot of this data. So the first thing we're going to want to do is come over and turn our calculator on. And you should pop up on this screen. If you pop up on a different screen, then maybe come back to this screen. And then the first thing you're going to want to do is hit Stat. And then you could either push 1 since it's the first item on the menu, or since it's already highlighted, you can press Enter. And I have already entered in the data points for this specific table. Note that it says it's the year, the input is the years since 1996. So you want to go ahead and calculate those. Don't enter in the actual year. So for example, 2006 is 10 years after 1996. So that is why there's a 10 right there. And then I also entered in the output values. So once you are here, you want to make sure that your graphing calculator is set up so that it will display your scatter plot. So what you want to do to make sure that that's the case is hit second and then here, because we're trying to get stat plot, and you want to press enter so that this right here, it indicates that it is on. So if I press enter, then we have these settings here. If your calculator is off, then you just want to switch it over to on. So you move your arrow over, and then once it's on, press enter. And then you also want to make sure that your X list is L1 and your Y list is L2. And if that's not the case, then go back down, and here is the L1. So you can press second and then L1 here, and then that will change that. Everything else you want to leave alone. So then we'll go back to stat, press enter, and to just look at our data table and make sure that that's accurate. It looks good to me. So from here, I think we can press graph. Oh, I forgot a step. So I'm going to go back to y equals and clear any functions that I have entered here so that that doesn't show up on our graph. So I'll press graph again. Another thing is it might not be showing your window like this, and so you want to edit your window settings. So if you click window here, what that will do is that'll bring you here, and you can edit your minimum x value, your max x value, your minimum y value, as well as your max y value. The other ones you just want to leave alone. And so if I wanted, I could come down here and maybe I want to see up to 20. So I press enter. And if I graph that now it's changed a little bit, but look at that. So our graph is kind of curving up and it asks us what type of function will model this data the best. And it's likely not going to be the case that it's going to be linear because look at the way that it's increasing. From 1996 to 1998, it increases by 2 billion. And then from 1998 to 2000, it increases by 3 billion, and then 7 billion, and then 9 billion, and then 12 billion. If this was close to linear, those numbers would stay the same or roughly the same, but that's not what's happening. And we can tell that from the graph as well because it's curving up. However, let's just see how we would do a linear regression. So what you want to do is hit stat and make sure that your data table is correct. And then we'll go over here to calc. And here's a list of the different types of regressions that we can do. And if you go down to option 4, you can either hit 4 or scroll down to 4 and hit enter. And linreg is short for linear regression. So I can come down to 4, hit enter, and then just make sure it's on the correct lists. We want list 1 and list 2, and then everything else you can kind of just ignore, and then come down here to calculate and press enter. Okay, so our linear equation that we found, our line of best fit, is y equals ax plus b, where our a value is like 3.27, and our b value is approximately negative 1.19. Now, if you watched the previous video in Microsoft Excel, we said that r squared is kind of a measure of how good our function is that we have calculated. So this one's about 91, 92%, which is pretty good, but we could potentially do better. So let's go back. Well, actually first, the way that we can graph this on our graph to compare it against our scatter plot is what we could do is let's clear out of here and then click this button that says VARS. So click that, and then you want to go down to statistics and then go over to EQ and then go ahead and it's already on 1 and press enter there. Oops, I'm so sorry. That's not what we wanted to do. We want to go to y equals to enter our function in here. So after you've hit y equals, then we want to go to vars and then repeat those same steps I said earlier. Okay, so now our function is entered in there. So if we hit the graph button, our scatter plot should show up as well as that linear function that we found. So that looks like it's decent. However, I feel like we could get something that's a little bit more curvy. So I'm going to unhighlight that so that it doesn't appear on the graph again. And I'm going to go back to stat, and instead of doing the linear regression this time, why don't we try the quadratic regression? So I'm going to hit enter and then calculate that. And oh, look at that. Our r squared value here is like 99%. Almost, that number is very close to 1. So this is actually quite better than the previous function that we looked at. So let's graph that here. So I've unhighlighted the y1 equation. So I'm going to come down here to y2, and then I'm going to press vars, go to statistics, come over here to EQ, and then hit 1 so that that populates there. And then if I hit graph, that graph should show there. Look at that. That graph is really close to our data points. It's like almost spot on. So I would say here that from our graphing calculator, it appears that a quadratic function would model this scenario pretty well. It gave us an r squared value of about 99%. All right, so if we go to part B, it asks us to create an exponential model, and we haven't explored exponential functions too much in this class, but they are of the form a times b to some exponent. So it's asking us to create an exponential model for the number of water bottles sold in billions T years since 1996. It also asks us to round A to the nearest whole number and B to 4 decimal places. So just like we've been doing, I'm going to unhighlight that second function that we had. And we're going to go to Stat. Our table's already set up, so we're going to go over to Calc, and then the exponential regression is kind of lower on our list. It's number 10 actually, or maybe that's a 0, sorry. 0, EXPREG stands for exponential regression. So I'm going to go ahead and click that and calculate that. Okay, so notice the r squared here is 0.997. The r squared for the previous one on the quadratic regression was like 0.999, so this one is not quite as good as the exponential, or sorry, this one's not quite as good as the quadratic, but it's still pretty good. So we want to, and it asks us to round, so let's be careful about that. So I'm going to insert an equation. So f of t equals our a value, it asks us to round to the nearest whole number, so I'll put 3. And then the b value asks us to round to 4 decimal places, so that's 1.288. And then the last digit we're going to round up, so 8 to the power of t. So that is our exponential function that we found using exponential regression. Now, there are two components to an exponential function. There's the a value and there's the b value. It's kind of analogous to a linear function where we have y equals mx plus b, and we have m, which is the slope or the constant rate of change, and the b value, which is the related to the y-intercept, because the y-intercept for a linear function is the ordered pair 0, comma b. So here, in everyday language, a represents, we can think of it as like the starting point. And b is called the growth factor, because each year we are multiplying. In a linear function, we would be adding the slope, but in an exponential function, we're taking this number and we're multiplying it each time to get the following value. Okay, so A represents the starting point and B is called the growth factor. So in this specific problem, A equals 3 would represent that the starting sales of water bottles in 1996 was 3 billion of them. And then the B equals 1.2888 represents the multiplying factor for each following year. So for example, if we wanted to approximate how many water bottles were sold in 1997, 1 year after, what we would do is we would multiply 3 times our growth factor, since t would be 1, so we're only multiplying it 1 time to our 3. So this next part asks us to find the water bottle sales in 2010 using this model. So notice that we actually don't have it here, and so we want to try to predict it for 2010. Now, 2010 is 14 years after 1996. So one thing that we can do is we can use our calculator to look at that. So let's go over here to, I'm going to go ahead and delete these functions because I want to put in the exponential function that we found. So if I go over here to vars and hit statistics and then go over and hit that, let me just verify that this is the correct function. Yes, so we have the 3 times the 1.2888 to the x power. Okay, and then if I hit second and then the table here, then we can go ahead and see what the output values are for that function. However, remember 2010 is 14 years after 1996. So I'm going to come down here to 14, and based off of our model, we are estimating that in 2010 there will be, wow, that's quite a lot, like approximately 105 billion water bottles. So our model predicts that in 2010 there will be approximately 105.58 billion water bottles sold. All right, so the next question asks us, when will the US water bottle sales reach 150 billion? So it probably won't be that much after 2010, but one way that we could go about doing that is by looking at our table. And so if you can see here, it's going to be between 15 and 16 years after 1996. So, in the context of this problem, it's probably sufficient to say that the water bottle sales will reach 150 billion sometime between 2011 and 2012. However, in other scenarios, we want to be a lot more exact. So let me quickly show you how we would get a more detailed solution, or at least a closer approximation, instead of just saying between 2011 and 2012. So we already have our exponential function here, and I'm going to basically graph a horizontal line at 150, and then if we look at our graphs here, now notice my window setting is not going to show the other graph. So I need to come down here and change my Y max. And since we're looking at 150, maybe I'll change this to 200 and then graph that again. So there are my data points. There's the exponential function that is our model. And then hopefully, there we go. It graphs our other function there as well. And with our graphing calculator, we can actually find where those two things intersect, and then whatever that x value is, it's going to tell us when it'll reach 150, and we should know that our answer should be somewhere between, what was it? It should be between 15 and 16. So if we don't get that, then we probably made a mistake somewhere. So the way that we do that is by hitting second and then calc here. And we want to find where they intersect. So you want to come down to number 5 and then press enter. And then it asks you to select the curves, but since we only have 2, the exponential, we could just press enter, and then the second curve is our horizontal line here, which is 150, and then press enter, and then it asks you to guess where they intersect, but really, as long as you're like not super far away, if you just hit enter again, it'll give you that point of intersection. So here it's telling us that the x value is 15.38, So if we wanted a more exact solution, which we probably should be more exact, so we can say, according to our exponential model, US water bottle sales will reach 150 billion approximately 15.384 years after 1996.